just use example to introduce these two things, antiderivatives and antidifferentiation. Antidifferentiation is reversing the derivative. So I think Word is suggesting pretty much nicely that what it means, antiderivative is resulting functions. So for example, if I differentiate sine x and you get cosine x, this is the result everyone knows, then we say sine x is what of cosine x? What do you think the correct word was? Antiderivative, and antiderivative. Make sense? Backward. And antiderivative is a function, right? And this process of computing from cosine x to sine x is an antidifferentiation. So the antidifferentiation. Soon this word will be replaced with integrals, integration, but at this stage this is the right word to use, right? Make sense? So antidifferentiation is an action, or in mathematics is called operation, and cosine x is sine x here is antiderivative, right? Can you find another antiderivative of cosine x? That's right. Plus 1 sine x is an antiderivative of cosine x, right? Not cosine x plus 1 or cosine x plus x. Cosine. If you differentiate this one, right, you get cosine x back. Is that right? So there's one more because 1 doesn't matter. Fair enough? Alright, so there are more than one antiderivatives. So that's my introduction to definition of antiderivative, antidifferentiation. Fair enough? Alright. Why is this important? I think a physics problem is that if you start with a position st, position at time t, and what is the derivative ddt? Get the velocity. And if you differentiate one more time, you have notion of acceleration. Is Newton's law of motion this is directly proportional to force that is acting on that total force exerted on that object at the same time. So if we set out a principle in physics, this is the source of force, gravity, this is electric forces, and it's whatever the friction forces. Forces is how we understand, right? The source of the forces is directly proportional to the acceleration. Then using mathematics, you go back and predict its location. That's the whole business of the beginning of the classical physics, right? We have understanding of the principle about how the force is interacting. We translate to the using Newton's law of motion to acceleration. Acceleration using mathematics, go back like that and figure out where it is, right? That's the whole business. And this part is called differential equation. Alright? It's equation through derivative, doing backward and things like that. So, for example, here's a typical question of differential equation. I didn't give you f of x and really ask you to figure out what 1 over 1 minus root x squared is. Does anyone remember this? What function has derivative 1 divided by root 1 minus x squared? That's a differential equation, right? That's a differential equation. So suppose, our forces is like behaving just like this function. What could be the velocity? What could be the next step, which is what could be the position of this thing? So who remembers an antiderivative of this one? Tangent, close, very close. Sine, even closer. Right, it's an inverse function. It was a sine inverse x. There was a section differentiating an inverse function. There we encounter that one. But this guy shows up again and again in classical physics and in the classical problem setting. So we found one, and how we find another one? Add some numbers, right? That's easy way of finding it, but it's a nice question. Can there be some antiderivative that we haven't found yet, right? It's a fair question, right? These are obvious that if you add 5, there's still antiderivative. Could there be more? Right? That's a typical question mathematicians ask. But if there are more, then it's important. If there are more solutions than what we understand, that your prediction in physics problem is a problem. It could be the other one, right? Not this one. But if mathematics says that this is the only one, then you have assurance that, oh, the physical system must follow this function. So it's very important to understand that these are the only solutions. Or is it? Alright, that's why we're doing this antiderivative business. That's probably the beginning of this whole calculus business. So, this is an important example. So let's do this exercise. So we're going to notation for this antiderivative. We have notation for derivative, d dx. So what could be these nice notation for this antiderivative? So we're going to do this as an exercise to understand this. Oh, is that? That's right. Stretched as symbol, right? It's a sum, and that's a stretched. That's integral symbol. But let's understand this one first. Describe all function f of x defined on negative pi over 2 to pi over 2 such that its derivative is 0. Probably it's going to take 10 seconds or 15 seconds. Very simple exercise. Go and write that down. Be serious. But what's the answer? Any constant functions. All constant function, right? Piece of cake. Alright. Second exercise. I want you to compute the derivative of this guy. That's exercise number 2. We just looked at some facts about the derivative of sine inverse x, right? Yeah. Hope you remember the derivative of cosine inverse x. Then it's just easy. If not, it's going to take a long time. Do you remember what the derivative of cosine inverse x was? If you use Mathematica or Wolfram Alpha, it says 1 over negative 1 over square root of 1 minus x squared. So that's the antiderivative. Right? Suppose you flip back and looked up the method of computing the antiderivative, the derivative of inverse function, and suppose you figured that out. And then you got answer what? 0. Very good. That's exercise number 1. This is exercise number 2, right? Because these two quantities are the same, right? Subtract equal to 0, right? Yeah, it could happen. It could happen. The third one is open-ended question. Alright, I want you to stare at this exercise number 1 and exercise number 2 and kind of write down your own thought, or if you're very strong math person, maybe you can draw a logical conclusion. Alright, certainly this conclusion or your thought is not boring. This is very interesting, right? Were you bored or interested in here by looking at these two examples? It's interesting, right? Why is that? Because we concluded that anything that derivative is 0 must be constant, right? But this guy doesn't look like constant function, is it? So what was your answer? Can you share your answer, some of your answer? Your thoughts? That's a well-trained kind of answer. So he was if you firmly believe in, there's no other way, by just drawing the picture a million times, there's no way the derivative being 0 and function is not being constant, like drawing the picture, right? If you firmly believe this is true, must be constant, and your correct conclusion is that this function doesn't look like constant, but it must be a constant function. Does that make sense? If you don't believe that one, then you will say, oh, I found one that doesn't look like constant function. So maybe I was wrong. We were wrong. All function must be constant. No, I found one. It's derivative 0, but it's not constant, right? Or maybe this is absolutely true, so it doesn't look like a constant function, but it is actually a constant function. So later, what Andrew derived is the correct conclusion. If you believe this, it depends on what you believe, right? If you believe our answer to the exercise number 1 is absolutely correct. Okay, there is a complicated web of trigonometric identities out there, right? Who knows? There's this massive function to take the derivative rules, simplify as much as you can take 3 days, became 0. And then you're looking at it. See, that's not constant. But if this is true, we already again conclude that, okay, it doesn't matter how massive it looks like, must be a constant function. So here's a picture of it. That's the derivative of sine inverse, and this is cosine inverse. So we add them, it's 0. And I actually sketched the arcsine plus cosine inverse, and what do you see? Horizontal line, which means it's constant function. All right. So if it is between negative pi over 2 and positive pi over 2, you can call that angle theta. You can call that angle alpha and beta. You can actually show that using the trigonometric identity, and you can actually show that this thing is actually equal to pi over 2 right there. The answer is pi over 2. Yeah. So let me state that. The correct fact is that sine inverse of x plus cosine inverse of x, doesn't matter what your x is, this is always what number? Pi over 2 for x coming from the interval negative pi over 2 to positive pi over 2. Now I was wrong. This is supposed to be negative 1 to positive 1. Negative 1 to positive 1. X is coming from negative 1 to positive 1. Sorry about the mistake, but that number pi over 2 is correct. All right. I think that's a serious example that makes you think about concluding something that is quite tempting in here, right? And there is an example that makes you think about, right? But the theorem that I'm about to introduce here is that if you have two functions and with antiderivative the same thing as it being the 0, and they're all constant, that is summarized in here. So I'm going to introduce this as an important theorem here. This is actually a theorem. If you have derivative 0, an open interval, it must be a constant function, right? That can be rewritten into that result that I just showed you. All right, and proof of this theorem uses mean value theorem, and it is also something important result is usually thoroughly introduced in Calculus 1 course. All right, now notation. I'm going to come back to those theorems that I showed you again. So let's just focus on notation. And